Hey guys, how's it going? Mr. Mitchell here. In this video we're going to start looking at special relativity from the ODU topic, and in particular we're going to look at reference frames and relative velocity. So let's get started. We're going to start by looking at the definition of a frame of reference. So it says here that a frame of reference or reference frame is a point of view from which an observer can measure physical quantities, for example distance, velocity and time. We will deal with different events taking place, hence we use the term observer to mean someone that is viewing the event. So both you and I would be an observer if we were viewing something taking place. And you and I would also have different frames of reference because we have different points of view viewing an event. It then goes on to say that most often these observers will be in different positions and moving relative to one another whilst viewing the event, and will therefore obtain different measurements of physical quantities depending on their location, for example space or earth. So more often than not, what you'll see in higher physics questions to do with this topic is one observer moving in space, for example on board a space shuttle, whereas the other observer will be on Earth. We're now going to see what is meant by classical relativity as opposed to special relativity. So classical relativity can be used to explain the motion of most objects in everyday life. For example, a ball kicked at 6 meters per second or a car driving at 70 miles per hour. So most of the physics that you will have done up until this point will have involved classical relativity, where you're looking at the motion of balls and vehicles and just standard everyday objects. But this section is all to do with special relativity, and we're going to see how this differs. And it says here that relative velocity involves the measuring of velocity by observers in different frames of reference, so your different points of view. Remember, velocity is a vector quantity, so we must take into account the direction of travel. And just to help you visualise this a bit more, I'm going to show you an animation. So here we have a train, and we've got a girl that is going to be walking along the train. So let's say our observer is not on the train and is standing to the side. So if I click play here, you'll see the train is moving at 20 meters per second, the girl moves at 5 meters per second along the train. So according to this observer, they're going to appear to be travelling at 25 meters per second. But let's say the observer this time is sitting on board the train, and the girl is going to move at the same speed at 5 meters per second. So if I click play here, you'll see the girl is still moving to the right at 5 meters per second, and because the observer is now on board the moving train, they are going to observe the girl to be moving at the speed that they're doing on the train. So that is simply 5 meters per second. And lastly, let's just assume we had another observer that was standing on a platform at the side, and they were observing what's happening on board the train. Well, if I click play here, because the train is now moving to the left at 20 meters per second, and the girl is moving to the right at 5 meters per second, they would see the girl moving at 15 meters per second to the left. And we're now going to consider a specific story just to help you understand relative velocity. So imagine you're on a train from Ayr to Glasgow for a night out, whilst listening to your newly made Spotify playlist Spotifying. The train is travelling at 60 miles per hour. According to the annoying passenger next to you who keeps making small talk, you're stationary. As the train approaches the nearest station without stopping, an angry old man standing on the platform sees you travelling at 60 miles per hour towards him as he makes rude gestures at the train driver. Later in the journey, another train is travelling in the opposite direction to you at 60 miles per hour. You see your physics teacher wave at you, and according to them, you're travelling at a whopping 120 miles per hour. This is because you're already travelling at 60 miles per hour towards the other train, and it is travelling at 60 miles per hour towards you. So we've got three different scenarios here. We've got the person next to you on the train sees that you are stationary from their frame of reference. We've got an observer who is not on your moving train, and he is stationary on the platform, so he sees you travel at 60 miles per hour towards him because you are on that train which is travelling at 60 miles per hour. And lastly, we have your physics teacher who is coming towards you at 60 miles per hour, and because you are going towards them at 60 miles per hour, then you both see each other travel at 120 miles per hour. So going back to the notes now, we have two rules that we can come up with for relative velocity. And it says that if the observers are moving towards each other, we simply add the velocities. So our relative velocity v would equal v1 plus v2 if we had two objects moving. Whereas if the observers are both moving in the same direction, then we can subtract the velocities to find the difference. So to find the relative velocity in this case for the two objects, we would do v equals v1 minus v2. It then says now consider another story, so I'm going to take you through this. So imagine you're on an interstellar train on the exact same journey as before, and just by coincidence the absolute anthem Rocket Man comes on. The train is travelling at 2 times 10 to the 8 meters per second. Again, according to the passenger sitting next to you, you're stationary, so that's the same as before. The angry old man standing on the platform sees you moving towards him at 2 times 10 to the 8 meters per second. Again, just like before, it's the speed of the train that the old man will see you moving at. Finally, according to your legend of a physics teacher on the other train which is travelling towards you at 2 times 10 to the 8 meters per second, you are travelling at 4 times 10 to the 8 meters per second. But alarm bells should be ringing here because it says, however, an object cannot travel faster than the speed of light in any reference frame, so the observation made by your physics teacher is impossible. So what's going on here? Well, when we deal with objects moving at relativistic velocities, i.e. close to the speed of light, classical relativity breaks down and we must consider special relativity instead. So this speed of 2 times 10 to the 8 meters per second is considered a relative velocity. So basically when objects are moving at everyday speeds, like cars moving at 70 miles per hour on a motorway, or balls being thrown at say 5 to 10 meters per second, then those fall under classical relativity. They are classical velocities, whereas relativistic velocities are those close to the speed of light, and we therefore need to consider special relativity. Lastly, it says to note that relativistic speeds are speeds greater than about 10% the speed of light, which is greater than 0.1 c, where c is the symbol for the speed of light. And non-relativistic speeds are speeds less than about 10% the speed of light, which is less than about 0.1 c. And so the cut-off speed that you should be thinking about here is 3 times 10 to the 7 meters per second rather than 3 times 10 to the 8 meters per second. So we're saying that relativistic speeds tend to be those above about 3 times 10 to the 7 meters per second, whereas non-relativistic speeds are speeds less than about 3 times 10 to the 7 meters per second. And just to help you visualize this story a bit better, I'm going to show you another animation. So imagine you're an observer sitting on a train and there's some source of light being projected on board the train, like a torch or something like that. Then when you look at that light on the train, you would observe it to be travelling at 300 times 10 to the 6 meters per second, or in other words 3 times 10 to the 8 meters per second, the speed of light. And if we click play there, that's fine. No matter what the speed of the train, you would still be observing that light to be the same because you're in its frame of reference, you're next to that source. Whereas if we now consider you to be an observer on the ground and the train with the light source on it is going to be moving past you, then it would look something like this. So you've got the train travelling at 20 times 10 to the 6 meters per second, or 2 times 10 to the 7 meters per second, and you've got the light going to the right as well at 3 times 10 to the 8 meters per second. Then in this case, because the two are moving in the same direction, you as an observer off the train would observe the light to be travelling at a speed greater than the speed of light, which is not possible. This is where we take into account Einstein's theory of special relativity, because this is going to help us explain how this is possible. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to subscribe and give the video one of these, and I'll see you in the next one. Take care.